Hi folks, this video is going to focus in on the second issue we have with identifying horizontal transformations. So if we just go back for a second and see if we start with some parent function f at x and we transform it by operating on the x variable, we saw that the effect of this on the x component of the original function is the opposite operation to what we see here. So if we have 2 times x as our new input, the effect on a point xy on the parent function will be to divide the x component by this factor here 2. Or if we had x minus 2 in the input, the effect on a point of our parent function would be to add 2 to the x component. So always the opposite effect. Okay, but there's another issue we have. What if we've got more than one transformation on our parent function? Okay, so say for example we're looking at the function square root of 2x minus 6. Okay, so this would be a particular example of this type of transformation. So if we take a look at this and we just go by what we've seen so far, we know the order in which we perform these transformations is important. So we might say that there is a horizontal compression. Okay, so remember, always the opposite effect. This times 2 actually would become a compression by a factor of 1 over 2. So this would be a horizontal compression by a factor of 1/2. We'd be multiplying all the x values by 1/2, and we would assume that we have a horizontal translation 6 to the right. Again, we see minus 6, but we know that the effect on the x component is to move to the right by 6. In other words, add 6 to the x components. Okay, but if we took a look at a particular example, okay, so again we would expect that this point 4, 2, the 4 would first be divided by 2, so, and then we would be adding 6. So this point here presumably should become the point 8, 2. Okay, but when we put in 2x minus 6, we see that that's not the effect. Okay, we see that the curve hasn't been moved to the right by 6 units, but it looks like it's only been moved to the right by 3 units. Okay, so we're going to have to explain this apparent discrepancy in what we're seeing. Okay, so let's take a look at why this does not work. Okay, so let's do what we've done before. Let's take a particular point on our parent function. Okay, so here our parent function is root x, and again we'll take the point 4, 2. Okay, and now let's consider the function f at 2x minus 6. Okay, so remember, going by what we saw before, we would think that the point 4, 2, okay, would first be affected by the horizontal compression, so that this would become 2, 2, divide x by 2, and then once we apply this here, we would expect the x component to be increased by 6, so 8, 2. Okay, this is what we might expect based on what we saw before. But when I actually go through with the algebra, so here these transformations are all horizontal, so I'm going to keep the y component constant. Okay, that means that this input here, 2x minus 6, needs to be equal to 4. And when we solve this, 2x, 4 plus 6, then x is equal to 10 divided by 2. We end up with x needing to be equal to 5. So certainly not what we found before. Okay, so we're going to explore this a little further, because remember, in the end, our goal is to be able to determine these new points by considering them as transformations of our original parent function. Okay, and in this process here, I notice a little problem that doesn't jive with what we were looking at before. Okay, in solving this equation here, I see that the first operation I performed, okay, when I brought the 6 over to the other side, was the additive operation. But when I'm considering transformations, I want to consider the multiplicative transformations first. Okay, so if I want to first consider the effect of the 2, so now we're going to redo this here. Okay, if I want to consider that multiplicative transformation first, in other words, I need to divide both sides by 2. I'm not just dividing the 2x by 2. I need to divide the whole left side by 2. And then, of course, the whole right side by 2. But when I divide the left side by 2, I end up with x minus 3. Okay? So now when I go ahead and do my additive operation, I see that I'm not adding 6 anymore. I'm actually adding 3. Okay? And this fits with what we saw in our graph. Because now let's take a look at this here. Look at our final point. When we keep the y value constant, the new x value is equal to 5, as we just found. So we can think of it here as first we're doing our horizontal compression by a factor of 2. So this 0.42 becomes 2, because I've divided the x value by 2. And now the second additive operation is adding 3 to the x component. Okay, so which brings us to 5. Okay. Problem is that's not necessarily very obvious in looking at the input of this function. Okay, so we're going to see if we can write that input a little differently so that the operations or the transformations that we're actually performing are a little clearer. Okay, so I want to come back to this idea here. Okay, and an alternative way for writing these steps, okay, is instead of first dividing both sides by 2, I'm just going to rewrite this left side by factoring it. Okay, I haven't actually changed anything. The only thing I've changed is the format. Okay, and once I write it in this form here, and I solve my equation by regular opposite operations, so the opposite of bed mass, I see that I'm performing the multiplicative operation first. So first I'm dividing both sides by 2, okay, which corresponds to my horizontal compression, and then I am adding 3 to both sides, so I'm performing my horizontal translation next. And of course I get the same required x value. Okay, now in the end, these two ways of solving are equivalent. But what's nice about first factoring the expression, so instead of writing f at 2x minus 6, I write it in an equivalent form, f at 2 times x minus 3. What's nice about considering this format is that I can read off the correct transformations on the function f. I read off here that I'm performing a horizontal compression by a factor of 1/2, and then I'm performing a horizontal translation by 3 units to the right. Okay, so in other words, when I'm considering horizontal transformations, I always need to make sure that the input is in factored form. That if I want to correctly identify the transformations just by looking at the numbers that are operating on x, I need to have it in factored form. So for example, if I have this function here, y equals, and say we'll use a cubic now, so let's say I've got negative 3x minus 9. Okay, this doesn't represent reflection in the y-axis, horizontal compression by a factor of 1/3, then a shift of 9 units to the right. Okay, I need to, oh sorry, I forgot the cube here. My first step in order to correctly identify the transformations is to factor the input. So here I can factor out the -3, and I'm left with x plus 3. Now I can correctly identify the transformations. So we were correct in a reflection in the y-axis. We were correct in the horizontal compression by a factor of 1/3, but now we can correctly identify the horizontal translation of 3 units to the left. Said earlier, 9 units to the right. Okay, so in order to correctly identify the horizontal transformations in a transformed function, we have to make sure that the input is always in factored form. Okay, so that's the main thing to get out of here. We've shown why that needs to occur, but the main thing to get out of this is the pattern. So the input always needs to be in factored form. Do that, you always get the right answer.